Hello, my name is Guillermo Cuermo La Cara. I am a student in the Master of Science at Universidad Autónoma de Nuevo León, and I will present the poster entitled Photocatalytic Degradation of NAPROXEN and CIPROFLOXACIN in aqueous medium by using bismuth oxybromide with an iron incorporation. In introduction, water pollution resulting from human activity poses a significant environmental challenge for life and ecological processes. Emerging contaminants not typically regulated represent risks to human health and aquatic ecosystems. Advanced oxidation processes like heterogeneous phytoplankton are effective treatments in emerging contaminant removal through highly oxidizing species. Bismuth oxybromide is a photocatalyst with activity under visible light 2.75 electron volts. Its photocatalytic activity can be enhanced when it is modified with transition metals like iron by facilitating charge separation and reducing the band gap. In this work, the photocatalytic activity of the synthesized photocatalysis with different iron incorporations with iron nitrate, hematite, and magnetite was evaluated in the degradation of naproxen and ciprofloxacin through heterogeneous phytoplankton processes. Well, the method that we use first for the synthesis of the photocatalysis there is the following that is here. Bismuth nitrate is dissolved with the iron source in ultrasound for 30 minutes, then the acetic acid is added. A solution containing the bromine precursor and a sodium acetate is then added. It is kept in a stirring for 2 hours. After this time, it is allowed to extend for 1 hour. Subsequently, the solid is centrifugated and a series of washes are made. It dries at 70 degrees Celsius and recovers. Finally, materials are characterized by scanning electron microscopy, ultraviolet visible diffuse reflectance spectroscopy, atomic absorption spectroscopy, X-ray diffraction analysis, and Fourier transform infrared spectroscopy. Then, for the photocatalytic degradation of naproxen and ciprofloxacin was made using the material synthesized following their UV-vis degradation. First, in a small reactor, we have each contaminant that is placed at a concentration of 10 mg per liter. The pH is then adjusted to 3. Then we have the 0.5 grams per liter of the photocatalyst, and that is added and stirred in the dark for 30 minutes for each photocatalyst. After this time, it is placed in the solar simulator at an intensity of 30 watts per square meter, and samples are taken every 15 minutes for 2 hours. Each sample is read in the UV-vis spectrophotometer at a maximum wavelength of naproxen at 230 nanometers and for ciprofloxacin at 275 nanometers. Here we have the results. This table that shows the results of the characterizations made to the photocatalysis by different techniques. First, the size of the chrysalis was calculated by the Scherer equation, in which it is observed that when incorporating iron into bismuth oxybromide, there is a decrease in the size of the crystallite. In addition, the band gap energy of the materials was calculated through the function of Kubek-Almond represented in the top plot. The incorporation of metal ions such as iron can create energy levels within the material band gap, which produces a shift in a wavelength to visible regional values. The calculated data show a slight decrease in the band gap energy due to the low percentage of iron. All materials are activated in the visible region. Nitrogen physics absorption analysis was also carried out for the synthesized materials. The surface area was calculated by the BET method. The three iron materials have a higher surface area to the base material, so it has a relationship with the size of the calculated chrysolite. The smaller the chrysolite, the larger the surface area. Finally, the percentage of iron incorporated into photocatalysis was determined by atomic absorption spectroscopy. The materials of hematite and magnetite were observed near theoretical incorporation of 0.5% compared to the material with iron nitrate, where a very low incorporation of 0.02% is observed. Then we here in figure 3 the same images of the materials where flower-like structure are observed, assembled with nanoleaves with interstitial spaces with smooth plates are shown. No modification with iron is observed due to the low incorporation of iron. Then the diffractogram of the materials is observed in figure 4, showing the characteristic pattern of the tetragonal chrysolite phase of bromide oxybromide in the proposed photocatalysis. An increase in intensity is observed in planes 001 and 102 due to the incorporation of iron. Then the infrared spectrum of the synthesized photocatalysis is shown in figure 5. The same characteristic bands were obtained in all materials. The bismuth oxygen signal is around a wave number of 500. Other bands such as the signal around 3500 and 1600 centimeters -1 of hydroxyl are observed, indicating the absorption of water molecules in the material. In addition, the signal at 2400 corresponding to atmospheric carbon dioxide is observed. The bismuth band is finally marked around 1400 centimeters -1. Finally, in figures 6 and 7 show the degradation of NAPROXEN and CIPROFLOXACIN. The bromide oxybismuth with hematite catalyst showed better degradation in both pollutants compared to the other photocatalysis. As we can see, the red line shows better degradation in comparing to the other synthesized photocatalysis in both contaminants. And in conclusion, first we have the iron was eventually incorporated into bromide oxybismuth with co-precipitation method using hematite and magnetite oxides, resulting in a value close to the theoretical concentration of iron, 0.5% weight. Due to the low incorporation of the metal, no iron signals were detected in X-ray diffraction or FDR analysis. However, the band cap slightly decreased and the surface area increased compared to the unmodified base material. All the materials exhibited flower-like morphologies assembled with nanosheets synthesized by the co-precipitation method. And for the photocatalysis that is incorporated with hematite shows the best activity for the degradation of both contaminants compared to the other modified materials and the base material, attributed to a better charge separation. Here I have the references that we consult and the acknowledgements First, thanks to the authors for their collaboration, to CONACYT for the scholarship granted, to financial support of Proactive YNL project, and to the Laboratory of Photocatalysis and Environmental Electrochemistry for the facilities. And this is all, and thank you.